Hi, thanks for joining me. Today I'm going to be continuing my mini-series on Gaussian Quadrature. This is part 3. In part 1 I discussed inner product spaces, and in part 2 I talked about the Gram-Schmidt orthogonalization process, and in today's video I'm going to be proving an important lemma. So let's quickly go over what we did in the last video. We constructed a basis of pi n of x, i.e. the set of polynomials of degree at most n. We're going to call this basis, or this basis will have vectors phi naught, phi 1 all the way up to phi n, where each of the phi i's are functions of x, and in particular each of the phi i's are polynomials of degree I. Okay, so the degree of phi I of x is exactly I. Okay, and we also have the property that phi I comma phi j, which is the integral from a to b of phi I of x times phi j of x dx, is going to be equal to 1 if I equals j, and 0 if I and j are distinct. So they're orthogonal, but in particular they're also orthonormal, i.e. they're 1 when I and j are the same, but 0 otherwise. Now in today's video we're going to be working towards proving this lemma here. We want to show that phi k has k distinct roots in AB, where k is any number between 0 to n. Okay, so let's firstly prove a smaller lemma, and then we can get on to proving this big lemma. Okay, so here's a mini lemma I first need to state and then prove, so I can get onto my big lemma. Okay, so let q of x be a polynomial of degree at most k minus 1. Now remember, k is some number between 1, 2, 3, all the way up to n, or in this lemma I should say, k is a member of 1, 2, 3, all the way up to n. So this makes sense. So it's a polynomial of degree at most n minus 1. Then I claim that this thing holds that phi k of x comma q of x equals 0. So the inner product of phi k and q is 0. In other words, phi k and q are orthogonal. So let's go on to the proof for this. It's not too difficult. We just use the fact that this thing here, phi naught of x, phi 1 of x, all the way up to phi k minus 1 of x, is a basis for pi k minus 1 of x. Okay, so this means because q of x is in this thing here, this set spans pi k minus 1x. In other words, there exists alpha 1, alpha 2, all the way up to alpha k minus 1. Each of the alpha i's are constant, such that q of x equals alpha 1 times, I should start from alpha 0, alpha 1, all the way up to alpha k minus 1. So q of x equals alpha 0 times phi naught of x, plus dot 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 all the way up to alpha k minus 1 times phi of k minus 1 of x. Just squeeze that in there. Okay, so q of x can be written as a linear combination of phi naught of x, phi 1 of x, all the way up to phi k minus 1 of x. Okay, so then that means when we work out this inner product here, we get phi k of x, comma q of x. That's going to be the same thing as phi k of x, comma this thing here. So I'm going to write this as the sum from I equals 0 to k minus 1 of alpha I phi I of x. Okay, now because of the linearity property, I can bring this summation out the front of the inner product. So I can write this here as the sum from I equals 0 to k minus 1 of phi k of x times phi I of x, and alpha I here. Okay, so the sum from I equals 0 to k minus 1 of alpha I times this inner product here. There's supposed to be a triangle bracket there, but there's no space. But here's where the crucial orthogonality property comes into place. Because I is always between 0 and k minus 1 in this summand, it's in particular not going to be equal to k. And because k is not equal to I, this inner product here will be 0 because they're orthogonal. So we're just doing the sum from I equals 0 to k minus 1 of alpha I times 0. But of course alpha I times 0 is just 0 for all I. So we're just adding up a bunch of zeros. So this whole sum here is 0. And that proves our mini lemma, this thing here. Now let's get on to proving the big lemma. And that is that for any k, phi k of x has exactly k distinct roots in AB. Okay, so let's move on to today's main lemma. Let k be some integer in 0, 1, 2, all the way up to n. Then phi k of x, I claim, has exactly k distinct roots in AB. Okay, so this is really important, and we'll see why, I guess, in the next video. it's crucial to proving the fundamental results sort of Gaussian quadrature. But yeah, let me prove this. Let's first look at the case k equals 0. Well, when k equals 0, then phi k is just a constant function, because remember phi k has degree k, so in the case k equals 0, phi k is phi naught, which is a polynomial of degree 0, which means it's just a constant. But because it's a basis vector, it can't be the 0 constant, so it's just some non-zero constant function. So in particular, it has no roots on the complex plane, or no roots on the real line, and in particular, it therefore has no roots in AB. So it has exactly k, which is 0, distinct roots in AB. So that makes sense sort of trivially. Okay, so now let's focus on k being a member of 1, 2, all the way up to n. Okay, now what we're going to do is, firstly, I claim that there's at least one root in this interval here, and that's not too difficult to see. Remember, if we look at this thing here, 0 is going to be the same thing as phi k of x times phi naught of x. Okay, and the reason for this is, remember, the phi i's form an orthogonal basis, in fact an orthonormal basis, and because k is in 1, 2, all the way up to n in particular, it's not 0, so this thing here is 0. Okay, but if we write down the definition of this thing here, it's the integral from a to b of phi k of x times phi naught of x dx. Okay, but remember phi naught is just a constant function, so I can bring it outside to the front of the integral, so I'm going to write phi naught of x as just phi naught, it's just some constant number. So you get 0 is equal to phi naught times the integral from a to b of phi k of x dx. Okay, but remember phi naught is non-zero, so I can divide through by it, so I can conclude that the integral from a to b of phi k of x dx is 0. Now, why does this mean that phi k has a root in AB? Well, suppose phi k didn't have a root in AB. Now, because phi k is nice and continuous, if it doesn't have a root, that means it's going to maintain sign. So either phi k is always positive, or phi k is always negative. If phi k is always positive, well then that means that its integral is certainly positive. But that contradicts this thing here, because we've shown that the integral is 0. And similarly, if phi k is always negative, then phi k would have integral being a negative number, but obviously that contradicts this thing here. So we must have that phi k has at least one root in AB. Now what we're going to do is use this to show, well, because we know that there's at least one, we're going to sort of try and work out, find some upper bound and lower bound, and in fact show that they're the same number, and thus conclude that the number of distinct roots in AB is exactly k. Okay, so we've just shown that phi k must have at least one root within AB, and in particular you can just sort of look at that argument again and deduce that not only is it a root, it's also a sign change. Okay, so phi k has at least one point where it changes sign between A and B. Now what we're going to do is suppose that it changes sign L times between A and B, and it changes sign at R1, R2, all the way up to RL. So let's just give a quick example. If we have our real line there, and A is there and B is there, and phi k, say, looks something like this. Okay, R1 would be this point here, R2 would be this point here, and we wouldn't have an R3. You might think that's an R3 because R3 is, at that point there is a root, sorry, but the sign of phi k doesn't change there. Okay, so R1 is the first point where phi k changes sign, R2 is the second point where phi k changes sign, and in this case we just have 2. And in particular, we have a repeated root here. Now we're going to show that having a repeated root for phi k is actually impossible, but for now we don't actually know that. So this is our notation, and yeah, what we have is L must be less than or equal to k. Well, why is that the case? Well, remember phi k is a polynomial of degree k, and thus has exactly k roots on the complex plane, and thus can only have at most k roots between A and B, and each of these i's are roots. So the number of sign changes is going to be in AB is less than or equal to the number of roots in AB, which is going to be less than or equal to the number of roots on the complex plane. So we get L is less than or equal to k. Now what we want to argue is that L must be at least k, and thus we can deduce that L equals k, and thus we have L different sign changes of phi k within AB, and thus phi k has exactly k distinct roots in AB. Okay, so to do that we're going to construct a polynomial q of x, but to do that we're going to firstly define si to be equal to, or first we'll have s or s naught, sorry, to be the sign of phi k on A R1. Okay, what do I mean by this? Phi k has constant sign on AR1, so either phi k is non-negative or it's non-positive, but for now we'll just think of phi k either positive or negative, so it has maintained sign, and thus the sign on this interval here is either going to be positive or negative, and thus this sine function here is either 1 or minus 1. Just in case you haven't seen the sine function, it's not the trigonometric sign. We simply say sine of x equals 1 if x is bigger than 1, bigger than 0, sorry, or minus 1 if x is less than 0. And for now we don't define it at x equals 0. For the purposes of this proof, we don't care. So it's 1 if x is positive and minus 1 if x is negative, and it's well defined on this interval here because phi k has the same sign on this interval here. Okay? So S0 is going to be that thing here, and then we're going to have Si is going to be equal to the sine of phi k on Ri plus 1. Okay, and we're also going to then have SL is going to be equal to the sine of phi k on RLB. Okay, so it's simply the sine, so S0, Si and SL. So Si, of course, is defined for 1, 2, 3, all the way up to L minus 1. It's simply going to be some number between 1 and minus 1, and that represents the sine of phi k between those two sign changes. Okay, and I guess you can also have the S0 is equal to minus S1, which is equal to S0 is equal to S2 is equal to S4 and so on, and S1 is equal to S3 is equal to S5 and so on. So S odd is equal to minus S even as well. Anyway, I'm getting lost here. Now what we're going to do is construct a polynomial, which I'm going to call Q of x. Okay, let me rub this off. We remember what the SIs are. Q of x, and this is going to be the product from I equals 1 to L of x minus Ri. So in other words, we're going to deliberately get our roots out of this and then multiplied by Si. Okay, well what's this going to do? Well, let's look at x. Firstly, this is a polynomial of degree L, quite clearly, because Si is just some constant, and each of these terms are linear in terms of x, and we've got L of them, so we're going to get L linear factors of x multiplied together to give us a polynomial of degree L. Great. Now also, if we look at this thing here, when x is a member of Ri plus 1, this thing here is positive, and this thing here has the same sign as phi k. Okay, so in particular, this function Q of x, no matter where you are within AB, has the same sign as phi k of x. Okay, and what this means, or what this tells us, is that the integral from a to b of phi k of x times q of x dx is strictly positive. Because these two things have the same sign here, so when you multiply them together, it's either going to be a negative number times a negative number, which is going to give you a positive number, or a positive number times a positive number, which is going to give you a positive number. So when you multiply these two functions, you get a non-negative function, in fact, strictly positive. It's non-negative, but because this, it's non-negative, continuous, and it's not 0 everywhere. So this means that this integral here is going to be strictly greater than 0. Now what we're going to do is use our previous mini-lemma to finally arrive at a conclusion about Q, and then we can deduce that L is bigger than or equal to K, and then we'll be done with our lemma. Okay, so I just proved that this thing here holds the integral from a to b of phi k of x times q of x dx is greater than 0, but in particular it's non-zero, and also by definition of q of x we can see that the degree of q is L. Now remember, by our mini-lemma, if we have a polynomial q of x which is degree less than or equal to k minus 1, then the integral from a to b of phi k of x times q of x dx is 0. And thus, sort of by a contrapositive argument, we can deduce, because we have this thing here, it must be that the degree of q is bigger than or equal to k, because again, if the degree of q was less than k, then this integral here would be 0, but of course that would contradict the fact that it's greater than 0. We'd get 0 is greater than 0, which is absurd. Okay, so we get the degree of q of x is bigger than or equal to k, but remember the degree of q of x is just L, so we can conclude that L is bigger than or equal to k. But remember before we had that L is less than or equal to k, so combining these two results we get that L is equal to k. Now remember L is the number of sign changes we have between A and B, so we can deduce that phi k changes sign at R1, R2 all the way up to RL, which is RK, but in particular it has roots at R1, R2 all the way up to RK. So phi k has k roots within AB, which are R1, R2 all the way up to RK, and that proves our lemma. Whew, that was a bit of a long one, a bit tedious, but it's not too difficult, and I think the proof is quite nice. I hope you have enjoyed it. Join me in the next one where we use this result and we can finally get to the big conclusion about Gaussian quadrature and solving our main problem. I'll see you then. Have a great day.